Now last class we did in electrochemistry, that is molar conductivity for strong electrolyte, we did it. And we got an equation at the end, Huckel-Debye-Onsager equation, we got it, which is nothing but cap m is equal to cap infinity m minus b root c, we got it, clear? Where cap m is the molar conductivity at a given concentration and cap infinity m was molar conductivity at infinite dilution. B is a constant and C is the concentration. We got this particular one. Up to this we have done it. Today we are going to do molar conductivity, or variation of molar conductivity in case of strong electrolyte, weak electrolyte. Alright, last class we did variation of molar conductivity with strong electrolyte, we did it. I took it KCl and I have explained it. Now today I am going to do variation of molar conductivity in strong, that is weak electrolyte, that I am going to do. Now see, same thing, what I am going to do is that here I am going to take, that is cap m, here I am going to take in the y-axis, and here that is root c into 10 to the power 4, I am going to take it. Clear? But I did it there, same thing. Now, it is a weak electrolyte. Now listen carefully, children, listen carefully. In case of strong electrolyte, I started from here, if you remember it. Alright, I started from here. Why? Because strong electrolyte dissociates almost completely. The degree of dissociation is large. But in case of weak electrolyte, I am going to start from here. Why? Because molar conductivity is less. Why? Because weak electrolyte dissociates feebly. It does not dissociate completely, dissociates feebly. So hence, for that reason, I start the graph from here. Got it now? In the previous one, I started from here because that was a strong electrolyte. It had got large number of ions, so molar conductivity was large enough. But in case of weak electrolyte, it dissociates feebly. Suppose if you take 100 molecules, in case of strong electrolyte, you will find more than 95 molecules will dissociate. But in case of weak electrolyte, hardly 15 to 20 molecules is going to get dissociated. So hence definitely the degree of dissociation is less in case of weak electrolyte than that of strong electrolyte. So hence in weak electrolyte, I am going to start from here. Now you know that the concentration is increasing in this manner. So dilution increases in this way. I told you last class. So when I am going to increase the dilution, what will happen? Suppose I am taking a weak electrolyte. Let us say acetic acid I am taking it. You know acetic acid is a weak electrolyte. It dissociates feebly. You have studied it. It's not a strong electrolyte. It's a weak acid. It's a weak electrolyte. It does not dissociate completely. So if I add water to the acid, what is going to happen? You will find the degree of dissociation is going to increase a little bit. Why? Because with dilution, the degree of dissociation increases. So hence, if you see the graph will be this sort of. You will be getting it, this sort of graph. See, it is increasing. This is for what I did, acetic acid as an example I have taken it. You can take any other example. So you can see it here, as I am increasing the dilution, the molar conductivity also increases. See, I am increasing dilution, the molar conductivity, the graph is rising up, the molar conductivity increases. Alright, now in this way the molar conductivity will increase. Alright, you can see it here, or you can say up to this much also you can take that. That, what you find, the dilution is increasing, molar conductivity is increasing. But, will it increase infinitely? No. To a certain extent it will do. If it does, then what will be the difference between a strong and a weak electrolyte then? What will be the difference between KCl and acetic acid? There is no difference between KCl and acetic acid on terms of degree of dissociation. Definitely there is a difference. KCl dissociates almost completely. Just now I said you, and acetic acid dissociates feebly. With increasing dilution, the degree of dissociation is increasing. As you can see, it is increasing. The graph is rising. But do you think it is going to rise infinitely? No. After that, if I draw the graph, I will be drawing this sort of graph. If I draw the graph, I will be drawing this sort of. That means I am drawing a dotted line parallel to y-axis. As you can see, I am drawing a dotted line parallel to y-axis. Now, what does it mean? Now, up to this much, what is happening? Listen carefully. Up to this much, when I was increasing the dilution, when I was adding water, the degree of dissociation of acetic acid was increasing. But as it is a weak electrolyte, it will not dissociate completely. Then after that, why the graph shows in this way? It still rises. Because after that, acetic acid does not dissociate. Water dissociates now. Acetic acid does not dissociate, the water dissociates. Alright, water is dissociating. So the graph which you can see in a dotted line, it is for the water. Alright, that is increasing. Understood now here? You know that my, what you can say, the case of study is what? Acetic acid. It's not water. So in a graph, you know, which I am not concerned in a particular graph, the substance which I am not concerned, I am doing with a dotted line. So hence I have done a dotted line here. So dotted line shows here that the molar conductivity increases, but the molar conductivity does not increase for acetic acid. It increases because water molecules dissociate further. For that reason it increases. But one more question here. Can you find the molar conductivity at infinite dilution? No. Why? Because what I said, here the molar conductivity increases, but it is a parallel line, parallel to the y-axis. Is it meeting somewhere? This line is meeting somewhere. Just like in the strong electrolyte, you have seen it that it was meeting somewhere. Here it was meeting. The graph was increasing and it was meeting somewhere. As I am increasing the dilution, it is going to meet somewhere. In the graph, theoretically, it is meeting somewhere. And I told you that it cannot be extrapolated. But here that also is not happening. It is not meeting somewhere. That means from this graph, you cannot find cap infinity M, that is molar conductivity at infinite dilution for acetic acid. You cannot find. Because if the graph will meet, then only you will find. Na? Suppose the graph will meet somewhere here. Let us say if it is meeting here. Yeah, I can say yes. This is a molar conductivity at infinite dilution. I can say that. But it is not meeting. It is a parallel line, as you can see. It will never meet. So from the graph, we cannot find the molar conductivity at infinite dilution for a weak electrolyte. This is the drawback of this particular graph. What I said, my topic was variation of molar conductivity of a weak electrolyte. But am I able to find the molar conductivity at infinite dilution for a weak electrolyte? No. I can find it at any particular dilution. That I can do it. That I can do. I can find cap M. At a particular concentration I can find. But my question is, am I able to find from this graph, will I get it? The value of molar conductivity at infinite dilution? No. Then what should we do? For that purpose, we require a law. Got it? Got the limitations of the graph? That what is the limitations of the graph? How do we find the molar conductivity what you can say, the variation of molar conductivity of weak electrolyte? You understood the graph, all of you? Now see, what I said, this is the limitations. We cannot find the molar conductivity in infinite dilution. Then what we need? We need to study another law. What is that? That is known as Kohlrausch law. Kohlrausch law. Now Kohlrausch law will tell you how to find the molar conductivity at infinite dilution. Kohlrausch law. Got it? What is the need of Kohlrausch law? Have you understood or not? Got it? So what is Kohlrausch law? Write the statement first. Right. According to this law, the molar conductivity at infinite dilution for a weak electrolyte. According to this law, molar conductivity at infinite dilution for a weak electrolyte is the sum of its ionic conductances of its cations and anions, is the sum of its ionic conductances of its cations and anions multiplied by the number of cations and anions present in the formula unit of the electrolyte. Multiplied by the number of cations and anions present in the formula unit of the electrolyte. Okay, now what I said? Kohlrausch law, molar conductivity at infinite dilution. This is molar conductivity infinite dilution. Is the sum of its ionic conductances of its cations and anions. Ionic conductance of cations is lambda plus and ionic conductance of anions is lambda minus. What is ionic conductance? I need to come to it. Now multiplied by the number of cations and anions. Number of cations is nu plus and number of anions is nu minus. This is number of cations, this is number of anions. This is the ionic conductance, let me put here. This is the ionic conductance of cations and this is the ionic conductance of anions. Let me give an example. See here. Suppose I have taken a weak electrolyte BaCl2. BaCl2 will dissociate to give you Ba2 plus 2Cl minus. Now, how many cations I am having for barium? Only one. So nu plus is here, how much it is? 1. How many chloride ions you are having? 2. So the nu minus is here 2. And the ionic conductance of barium will be given to you and the ionic conductance of chloride will be given to you. So if I need to write the molar conductivity at infinite dilution for barium chloride, how should I write? See, cap infinity BaCl2 is equal to, that is lambda infinity or lambda Ba2 plus, or lambda infinity also you can write. Now plus 2 into lambda Cl minus. This lambda or infinity you will know it otherwise. So lambda Ba2 plus will be given to you, means ionic conductance of cation will be given to you in the question. Ionic conductance of the anion will be given to you. You put the value here, multiply with 1, you will get the answer. You put the value here, multiply with 2, you will get the answer. Then you add it. You will get the molar conductivity at infinite dilution for a weak electrolyte. Alright, in this way we can find it out. Because from the graph you saw that was not possible, because the graph was a parallel line, parallel to the y-axis. So we cannot find it out from the graph. Then what you need to do? We can find it out in this way. For example, I took the example acetic acid. In the graph, I took it acetic acid. Okay, I'll write it acetic acid. See here, CH3COOH. Now before that, let me write the equation. CH3COOH dissociates to give you what? CH3COO minus plus H plus. So lambda infinity CH3COH is how many cations you are getting? 1. So lambda H plus. How many anions you are getting? That also 1. So lambda CH3COO minus. So once you put it, the ionic conductance of cations and anions, and you add it, you will get the, what you can say, molar conductivity at infinite dilution for acetic acid. In this way we find the molar conductivity at infinite dilution for a weak electrolyte, which was not possible from the graph. This is one of the application of Kohlrausch law. We have still 2 more applications. I am going to tell you in the next AV. Thank you very much.